Hi students, in this lecture I am going to discuss Ampere's law. Let us see what is it. So till now we have discussed Biot-Savart's law, and using that we made calculation for magnetic field strength. So now we are going to use Ampere's law. Right. See, we compare Biot-Savart's law with Coulomb's law. So we are comparing this with Coulomb's law. So Coulomb's law in electrostatics, right? By using this, we made calculation for strength of electric field, and we compare Ampere's law with Gauss law. So comparing Ampere's law with Gauss law, and we have seen that whenever distribution of charge is symmetric, then Gauss law makes a calculation very simple, right? Now exactly same logic here also. Whenever distribution of current is symmetric, calculation of B bar becomes very simple with the help of Ampere's law. Let us see first the statement of this. Let us consider there is a current I1. This is now towards us, means normal to plane of this board, and towards us current I2, that is into the board, and I am taking here one loop. This is one loop. Imagine one loop. Okay, and current I3 here, suppose inwards, current I4, it is outwards, means normal to plane of the board, and it is inwards and this is outwards. So here we are imagining one loop. Okay. Now see what it states. It states that closed integral b bar dot dl bar is equal to mu naught into net current passing through the surface bounded by the loop. You can see in diagram. This is now loop. Okay. This is a loop. Now this is the area bounded by that loop. Through that surface or through that area, how much current is passing. This is now outwards. This is inwards. Okay. Let us assume we are taking outward current as positive. Current outwards means if you are keeping the thumb outwards, curl fingers of your right hand, it is now anti-clockwise. So I am keeping an arrow on this loop anti-clockwise. Okay. Now I am taking one small element on this loop. Its length is now dl. Okay. And I am taking direction of dl bar is it is anti-clockwise. That means this is now direction of dl bar. So here you should be very careful. Earlier we have taken dl bar on the current carrying wire. But now here we are taking dl element on a loop which we are imagining. I am repeating. Earlier we have taken element on the current carrying wire, and direction of dl bar is direction of current. But coming to here, we are imagining a loop, right? And through this loop, there is no current. Now here what we are doing is take either outwards as positive or inwards as positive, which is our choice. So here I have taken outwards as positive. When outwards is positive, keeping thumb outwards, curl fingers of right hand. Now curling fingers, it is anti-clockwise. That's why I am taking an arrow anti-clockwise. Okay. Now I am taking a small element on the loop. This is now having length dl. And for this direction is, since we have taken anti-clockwise, it will be like this direction part. Okay. Now at this point, net magnetic field is B bar. So B bar stands for net magnetic field. That means resultant of the magnetic field due to all currents I1, I2, I3, I4. So B bar is net magnetic field. I am writing here B bar. It is field due to all currents. It is not just a current which are inside, okay? All currents means it is net field. Right. Now see carefully. At this location, we are taking B bar net value. So B bar dot DL bar for this part. Like this, we have to take all elements, small lengths on this loop and calculate B bar dot DL bar. Then we have to add all those things. That is integration. And remember this symbol here. This is a closed integral in the sense we are taking now integration over a closed path. Okay. It is over a closed path. That is equal to mu naught into net current inside the loop. In this, we can see net current means I1 outwards, I2 inwards. According to our convention, outwards positive, inwards negative. That means in this diagram, this net current is equal to I1 minus I2. Okay. This is Ampere's law. This is also known as Ampere's circuital law. Right? So circulation, or you can say closed integral V bar dot dl bar equal to mu naught into net current that is passing through the surface bounded by this loop, right? While taking this net current, you no need to take the currents which are outside, only inside. But B bar is due to all currents. See, this is same as Gauss law. Because if you remember in Gauss law, we have taken E bar dot ds bar equal to net charge inside upon epsilon naught. So in this net charge inside the Gaussian surface, but a field due to all charges means charges inside Gaussian surface, charges outside. Exactly same logic here. B bar is due to all currents inside and outside. But this net current is only the inside currents. Okay. Let us now focus how to use this. Okay. I am taking one example. Let us calculate magnetic field due to a long thin wire. Long thin wire. It is a straight wire. So I am taking that. It is now into the boat. So current is take it as I. This is now current is normal to this board. Let us take it as it is out of the board, right? We want to calculate at some distance r. What is now strength of the magnetic field? Okay. So direction of current is normal to plane of this board and towards us, right? So one thing we can guess here, at each and every point, at same distance r, strength of B bar will be same, right? So here what I am doing is, I am imagining one circle. So why circle means? Because for same distance, modulus of B bar will be same. So I am taking the loop shape. Shape of loop is circle. So how we are taking that? This current carrying long thin wire is passing through center of circle. That means each and every point on circle, their modulus of B bar same. Okay. And you can see here, if we are taking outwards as positive, then we should take anti-clockwise as positive. So I have to mark here arrow anti-clockwise. It is anti-clockwise. Since the current is towards us, keep the thumb towards us, curl fingers of right hand. That means now magnetic field is, I am showing here. This is correct carrying wire. Magnetic field lines will be concentric circles. Means we can see here concentric circles. This is now field line, okay? And this is one more field line. So when you are taking long thin wire, then magnetic field lines are concentric circles. And direction, you can see here, keeping the thumb along current flow. Means in this case, thumb is towards us, curled fingers of right hand. Curling fingers will be anti-clockwise. Therefore, arrow is now anti-clockwise. Suppose I want field at this point. Then tangent will be like this, direction of field. If you want field at this point, direction part, tangent will be like this. If you want field at this point, tangent like this. Okay. So field lines are concentric circles. So now coming to here, we want to calculate closed integral b bar dot dl bar, right? Suppose I am taking a small part. Its length is now dl. Okay. Now for this dl direction is, I have taken arrow here anti-clockwise. Okay. Direction is now like this. And direction of magnetic field, it is also, we can see right along same direction. So now what we can say, at each and every point on this loop, direction of dl bar, direction of b bar are same. That means between those two vectors, angle is 0. At each and every point, modulus of b bar is same. Therefore, see what I can do here. Closed integral b bar dot dl bar, that is equal to mu naught into, see how much current is passing through this area. That is I, right? It is I. So in this I am writing closed integral b into dl into cos 0, that is 1. Since b constant means modulus of b bar, right? Constant, take outside. closed integral dl, that is equal to, and we are knowing that if you add dl, again dl, again dl, add all these small lengths, then we are going to get 2 pi r, 2 pi r, which is equal to mu naught I from this b value. It is mu naught I by 2 pi r. Like this, we can use Ampere's law to find strength of the field. Okay, let us solve problems basing on this to get more clarity. Right, first of all, see the statement. The line integral or circulation of the resultant magnetic field. So this important one is resultant. Okay, it is line integral or circulation of resultant magnetic field along a closed path is equal to mu naught times the total current crossing the area bounded by the closed path, provided the electric field inside the loop remains constant. So your focus wants this sentence, why electric field should be constant. In fact, we are going to learn in next chapter, that is electromagnetic induction. Then we are going to learn changing electric field is going to produce magnetic field. But coming to here, we want to calculate strength of the field because of current carrying wire, right? That's why here electric field must be constant. That means magnetic field is only because of current carrying wire. If electric field is changing, that is going to produce magnetic field. Then this magnetic field and field due to current carrying wire, the net value will change. But here our goal is only to calculate because of current carrying wire, what is the strength of the field? That's why this condition here. Okay. See the first question asked for 2 marks in 1993. A current I flows along the length of an infinitely long, straight, thin-walled pipe. Then asking like magnetic field at all points inside a pipe, same but not zero. At any point inside the pipe, zero. Zero only on axis, different at different points inside. Condition given that a current I flows along the length of an infinitely long, straight, thin-walled pipe. That means it is hollow cylinder, right? Let us see how to calculate. So we are taking here hollow cylinder. This is now hollow cylinder. We can see length is now normal to plane of this board. That means for us, it appears as circle. Okay, I am repeating. Length is into the bow, right? And we have to see that current is now flowing along the length. Now we want to find the field inside. See what we are doing. First of all, we are taking a loop just inside. So taking a loop just inside. you can see through this loop, means through the surface bounded by this loop, no current is passing, right? That means when you take closed integral b bar dot dl bar, that is equal to 0. Why 0 means? There is no current in this region. Okay. And by symmetry, we can guess that at each and every point, modulus of b should be same, right? So what I'm doing here, closed integral b into dl into cos of the angle, that is equal to 0. I'm taking b outside. Remaining is now integration of dl. Okay. It is clear that this value is not 0. Getting it? This is not 0. That means only b should be 0. So from this we conclude that at any point inside a hollow cylinder, there is no magnetic field. Okay. Suppose if you want to calculate outside, if you want to calculate outside, so now this is a hollow cylinder. We want to calculate outside. Then we imagine the loop. So we have to imagine the loop outside. This is now loop. If you remember, while discussing Gauss law, we have discussed a spherical conducting shell where distribution of charge only on surface, then field inside 0, outside same as due to point charge. Now exactly same logic. Here field 0 inside. And when you want to field outside, it is same as due to a long thin straight wire. So replace this with a long thin straight wire along its axis. So where we replace that? Along its axis. Then distance equal to r. Then field equal to mu naught I by 2 pi r. So just by comparing with that Gauss law, what we got? Inside 0, outside same as due to point charge. This is now same as due to a thin infinite long wire. Okay. Or by symmetry, you can guess at each and every point modulus of b bar same. And direction will be along a tangent. Means concentric circles. Okay. Same as due to a thin straight wire. That means again we are going to get it is like b into 2 pi r, that is equal to mu naught I. Then we are going to get this one. Okay. So coming to answer. So 0 at all points inside. So it is 0 at any point inside the pipe. This is correct one. And remains C ones at all points same but not 0. This is wrong. 0 only on the axis. And that is wrong. Different at different points inside the pipe. This is also wrong. The only correct one is, it is option B, right?